The exercises should be in the Slack channel. I believe they're also on the website, but I can guarantee they're in the Slack channel. Great, I'm gonna go shut my door, make sure I don't get bothered, and then we can begin. Alrighty, how's everybody doing? Cool. So let me first start by sharing my screen. Can I get some confirmation that someone can see my screen?
Yes.
Okay. Cool. So as I mentioned first of all, actually, welcome back. Thank you for coming back for session 2. This is where kind of the fun stuff starts to happen, so I'm looking forward to it. Basic agenda for tonight, I'm going to start off by answering any immediate questions that any of you have about something we talked about last time, something we thought about, something unrelated, something about the small homework I gave you. If you have none of those questions, we're going to spend the first maybe third to a half of the session talking more about Python programming, Python syntax, how we do that. In doing that, we're going to both write some new code as well as go over that small homework assignment. So if you're just totally lost on that, we're going to go through how to do that. In doing that, we'll kind of review a lot of the things we talked about last time and just get more experience writing code. Then in the second half of the session, probably around the 1 hour mark, we're going to, as we did last time, shift gears, and we're going to start talking more about the data science side of things. Unlike last time, though, we're actually going to try and get our feet wet and do some data science. We're going to start playing with our Titanic data set that we mentioned last time. And we're going to start to make decisions, clean that up, and start just getting our getting our hands dirty and working with the data. So before we kick off with me talking, are there any specific questions about anything from last time, homework, or anything else?
Are we going to learn something about Hadoop?
This class is not going to cover Hadoop. I'm happy to kind of give a brief overview about what it is and, situations where it's useful, as well as give you some resources. But that's a bit outside of the scope of the class. And the reason is Hadoop is sort of I call it a power tool. It's something that it basically allows us to do a lot of the same stuff that we're going to be doing at a much, much larger scale, and we have much more data. So A, it's a bit unnecessary because our data in this class is very small. But B, while it's kind of a very important industry tool, it is, it's really conceptually not much different from other stuff that we're going to be doing. It just helps us do it at kind of industry or production scale, which we're not quite at yet. Any other questions? A couple seconds.
Well, I just joined. Have I missed much, or?
You missed absolutely nothing.
Oh, good. Okay.
I was asking for questions, and then we're going to get started.
Cool.
Cool. So if there are no questions, let me get started. Can you guys see the code? It should look exactly like it did when we left last time because it's the exact code that we had last time. Can everyone see? Great. Cool. So we're going to start off. I'm going to delete this code for the moment. We might come back to it in a little bit. We're going to start off by writing a very, very, very simple game. And in doing so, we're going to learn another new concept or two, as well as, sorry about my dog in the background here. We're going to learn another concept or two, as well as go over some of the older ones from last time. So the goal here is very simple. We're going to write a basic guessing game. We're going to ask our user for a number between 1 and 100. And then if the number is higher than the number that we are looking for, we're going to print higher. If it's too low, we're going to print too low. If it's exactly right, we're going to tell them they've won our game. Sounds very simple. In doing so, again, we're going to learn a new concept or two. So the first thing we're going to do is we're going to make a variable for our number that we're trying to guess. We'll call it num to guess. Right now, we're going to set it to 42 because I like the number 42. So does anyone remember the keyword for getting input from our user? So if I want to put
Raw input?
Sure. So we can say guess equals raw input. If I can spell, input, enter your number. And just to make sure that works, print guess. We can run our code. We can say enter our number is 5, prints 5. Great. And just for sanity, so we can see, we're going to print the type of our guess. And we can see that it's a string. So there's two things we can do to make this not a string. As we mentioned last time, we can switch this to just input, and it will guess the type for us. Or we can say raw input, and then manually tell the computer that, hey, we're dealing with an integer here. And when we do this, it should have the same thing. Great. So now we need to make a decision here, right? We have three options. Option 1, guess equals number to guess, user wins. Guess guess is less than number to guess, print too little. And then guess is greater than to guess, print too high. Great, so we're going to talk about a new kind of statement. If you're coming from another language, you're familiar with it. If not, it's pretty intuitive. It's called an if statement. Basically, what an if statement does is it says if this thing, if my statement is true, we're going to do one thing. And if my statement is false, we're going to do potentially something else. So the syntax is super easy. We can say if guess equals, and two equals, and I'll explain why in a second, num to guess. And then just like we indented things in a for loop to go multiple times, we can indent things in an if statement. We can say print, you got it. So we're going to run this just to make sure. So if we enter 12, it does absolutely nothing because we didn't get it. And if we enter the correct answer, 42, it prints out, you got it. So what the things you'll notice, one, there are no parentheses around this. Parentheses are optional in Python in if statements. They will, it'll work with or without it. But the more interesting thing to notice is the two equals. Does anyone have an idea why I put two equals instead of one equal sign here?
Referencing that it is equal to. Or
I think phrasing may be confusing, but I think you're on the right track. So the difference between two equals and one equals is two equals is a test for equality, and one equals is what we call an assignment. So if I have something equals something else, it sets the something to the value of something else. Just like here we have num to guess equals 42. It sets num to guess to 42. If we have two equals, this becomes an expression and it evaluates. So we evaluate either are these two things equal, and we actually make the comparison. Instead of setting, so if we put one equal, this would say if guess, it just sets them equal. So this is called, so this returns what's called a Boolean. A Boolean is a value that can be either true or false. And just to make it a little bit more clear what's actually going on here, we can say print guess equals num to guess. And when we do this and we print it out, we can actually see it's either going to print false if we're false and print true if it's true.
So it calculates because it's double equals.
Correct. It calculates. So all this is really saying, and we can make it a little bit more clear, we'll call it correct is going to be equal to that. And then instead of actually evaluating it there, we can say if correct. So correct is going to get set to a true or false. And then if it's true, we're going to print this. Otherwise, we're going to do nothing. So you can see this is going to work the same way. We do nothing here. We print 42. It says true. And I'm going to make this a little bigger. Any questions so far?
For the brackets around it, is that Python 3? It has to be, doesn't it?
Nope. That's only for print.
Right,
you can put with or without. Again, it'll work the exact same.
Cool.
Cool. So this is pretty useful. So now we can do this. And just like we can check some two things are equal, we can do other fun operations on them. So now we can say if guess is greater than the number to guess, print you guessed too high. And we can say a third one, if guess is less than num to guess, print you guessed too low. Cool. So we're going to test this. We're going to enter 10. We're too low. We're going to enter 50. We guessed too high. And we're going to enter 42. We got it correct. Any questions on any of this? So just like we have equals, we have less than or greater than. And just like we have less than or greater than, we can do this for less than or greater than or equal to, and less than for less than or equal to. Any questions?
No.
Great. So just like we have if, there are two other things that are often seen with if. One of them is called else if or elif. So I'm going to change these two to be elif, and then I'm going to run our code, and we're going to see that nothing happens differently. It's still 10 is still too low, 50 is still too high, and 42 is still correct. So can anyone who might have seen an else if statement before give me a definition of what's actually going on here and why I changed our code and nothing else is happening?
It's the same thing.
Yeah, exactly. So
it needs to be nested within the f loop, within the f construct.
What did you say? Sorry, I couldn't hear you.
The elif needs to be nested. It has to be indented. You know,
no, not necessarily. So let's actually look at what elif is doing.
Is it multiple sub ones?
So what the elif is actually doing is it said it's just like an if statement, but only gets there if the ones before it are false. So this code will never get run if we get the first one, or this code will never get run if we get the second one. To make this a little bit more clear, what I'm going to do is I'm going to say.
So if they're all if, then they all get run anyway, without the value being different.
Correct. So what I'm going to do to make this a little bit more clear is I'm going to say if guess is greater than number to guess times 2, print you guessed way too high. So basically what we're saying is if we guess twice the twice the right value, we're going to say your guessed way too high. So we're going to say 100, and then we say, hey, wait a second. We said we guessed too high, but we also said we guessed way too high. But if I change this one to an elif and say 100, we only run it once. So this one's true, so we don't bother guessing. We don't bother running this code.
So it just takes the first one that was true.
Correct.
Okay.
So if we actually wanted to write this code, we would switch the order of these, and then we could say elif here. So now it prints, if we're way too high, it prints way too high and not regular too high. And if we're regular too high, so let's guess 50, it prints too high. So it only is going to run this code if this one isn't true. So instead of saying each one's a separate if statement, elif let us kind of do fallbacks. Does that make sense?
Yeah.
And on the topic of fallbacks, the last important keyword here is else. What else says is, if we get to this point and nothing else has happened, we're going to do this. So we're going to say print, you guessed, too low. So this is actually going to end up the same as before, because if it's not equal and it's not too high, that must mean it's too low. So if we have kind of this default case here, we don't necessarily have to specify the exact condition. We can just sort of have a catch-all, if you will. Does that make sense?
Yes, you can have as many ifs as you'd like.
Yes, you can have as many ifs and as many elifs. The only condition is that the else has to be last.
Okay.
And if you do put another if, it breaks the elif chain. So for example, if I put if something here, then this elif belongs to just this if statement, not the ones above. Does that make sense?
Yeah, yeah. In that case, is there something like a switch case statement?
There is. Yeah, there is. It's very, very, very uncommon to use one in Python, though. To be honest, I'm not entirely sure why. It just seems that Python programmers don't like switch statements. They much, much, much prefer elif. The reason is switch, when you use it in like C, there's a lot of nice memory things and speed things it'll do. You don't really get them in Python. And a lot of Python programmers just think that it's less clear. So they tend to use ifs and elifs. Cool. So we're going to do now, this is a decent game. There are a couple things I want to change. The first thing I want to do is I want to keep track of how many guesses it took our user. The problem with this is right now our code only runs once. We get it, we say our number is too high, and then we have to run our code again. What I want to do is I want to run this code multiple times until we actually get the number. Any suggestions on how we might do that?
Put in a function.
We could. So we could. I'm going to hold off on that right now, but that's we're going to do that in a little bit. But I want to run the code multiple times when I run the program. I don't want to have to hit play every time.
Use a for loop.
Exactly. So let's use the for loop. So let's say for x in range, let's give the user 100 guesses. And then we're going to indent all of this. And now let's run it. Enter a number. Whoops, that's not quite right. Why is my computer not liking this? All right. So I want to put this statement inside of the for loop so that we can stop. Come on. So that my computer is not cooperating. So I want to put the guess in the for loop so we can actually get a new number every time. Great. Please open a new console. 2 + 2. We're good. Run. There we go. So we're going to enter number 10, too low, 50, too high, 42. Oh, we got it. But wait a second. It doesn't tell us to, it doesn't stop. So we want some way to exit when we get it. If we get the answer, we don't want to keep asking our user. So there are a couple ways to do this. We're going to look at a couple ways to do this. The first one is what's called a break statement. What a break says is basically, hey, exit the for loop. I don't care where you are. I don't care how many times I told you to run. When I say break, it exits now. So if we put a break right here and then hit play, we can guess our number. 10 is too low, 100 is too high. And then as soon as we get 42, it prints we got it, and it exits our program. Any questions?
No.
Great. So this is great. Now let's really quickly add support for how many times we had to guess. So print it took you, print it took you, and then I'll explain what this is going on in a second. X guesses. So now we're going to run this. Actually, so one small bug here. Since our for loop starts at 0 and we count by 1, we're going to say it took you X plus 1 guesses. So let's test this out. 2, 3, 4, 5 are all wrong. 42, it took us 5 guesses. That means we got it on our 5th guess. Great. So now our game is keeping track of how many guesses it took us to get it. I'm going to show you a little bit of a trick to make this look a little bit nicer. I'm going to put, so if you have a string and you put these little, you put curly braces in the string, what you can then do is what's called string formatting. And what string formatting is it says, hey, take the variables that I give to format and throw them into the string. So now what it says is take X and put it into where these braces are. You can see here this is actually going to work the same way. 1, 2, 3, 42. And it says, hey, it took us 3 guesses. We need our X plus 1 again. It's called an off by 1 error. 1, 2, 3, 4, 5, 6, 42. It took us 7 guesses and looks great. Any questions on that? Chat here. Cool. Any questions on that? Great.
If you wanted to have like 2 variables in one of those print statements.
Yep, you can. Guesses, so we can say to guess the number blank, and then we just pass it a second argument. We can pass it num to guess. So now we do that. We can say 142. Now it took you 2 guesses to guess the number 42. Is that what you're asking?
Yeah, that's so weird how that works out. So just in the order that those brackets are in.
Yes. So you're pointing out a very good issue here. And that is this can get, annoying is not the right word, but it can get a bit tricky if you have a lot of these. What you can actually do is you can actually put names in here. So you can say num guesses, and we can say num 2 guess, and then you can actually pass them by name. So you can say num guesses is equal to that thing, and then number 2 guess is equal to the other variable. And then it'll actually fill them in by name, so you can put it in any order.
Oh, it's just like another like variable assignment happening.
Yep. So it'll actually assign the variable in there. Just to show you, it do the same thing. It took you 1 guesses to guess the number 42. Any other questions?
Thank you.
Any other questions on this? Let me look over here. Cool. So there are a few more problems I have with this. What if our user is really, really, really bad at this game and it takes them more than 100 guesses? What do we do?
That'll be preference, the preference of the developer.
Sure.
Or
It's true, we can go ahead and change this variable. But I want to give you unlimited guesses. If you're really, really, really bad at this game, I never want to cut you off. How can we give someone unlimited guesses? Do we know a way?
While something is true, do it.
Exactly. So just like we have a for loop, the other big kind of loop that we have is called a while loop. So when we make a for loop, we say, do this thing n times, or do this thing once for every element in our list. What a while loop does is it says, while this condition is true, keep on going and keep on going and keep on going. So what we can say is while guessed is equal, we can say is false. So when you're comparing in Python to Booleans, you can just say, sorry, not to Booleans. Well, guessed is false. Keep doing that. So we'll have to make a variable called guessed, and we'll set it to false to start. And then instead of breaking here, what we can say is guessed is equal to true. So now this will go on forever and ever and ever and ever and ever, as we'll see. 10, 10, 10, 10, 10, 10, 10, 0, 10, -1, etc. And then as soon as we get it right, it will it will break out of our loop. So as soon as this thing becomes false, we get to exit our loop. So here now we have to keep track of the number of guesses for ourselves. So we'll call this, we'll make a variable called num guesses. And then here we'll just say num guesses plus equals 1. And we're going to set it off to 0 to start. So now we have, come on. So now we have 10, 42, and then it says, great, the number of guesses is correct again. Any questions there? That was a lot of code, I know, but it was just substituting out some variables. We just added this one for guest and one num guest. And when those are, as soon as guest gets set to true, wherever it is here in our loop, we immediately exit and go on. And then we can say, run the rest of our code, print U1. Any questions there? Switch over here. No questions? Great. So what would you say is a flaw in our game? Anybody have any ideas? How can we make our game better, maybe? Any guesses or suggestions?
You can help the user to guess faster by giving out tips.
Sure, we could give out tips. Not quite what I was thinking, but we could. We could say how far away they are or something along the lines. We could add more, you're high or you're way too high, stuff like that. But that's not quite it. So my big problem with our game is we are currently guessing the same number every time. We're always guessing the number 42, which I don't know about you, I don't find that very interesting. So, yep, exactly. Sorry, I didn't see that in the chat. Random number to guess. So the question is, well, how the hell do we get a random number? And the answer is we get to use a module. Does anyone have any a good definition for the word module? When I say that word, does that mean anything to you? So what a module is it's basically clock and math are good examples. In Python, it's actually called time, but that's sort of relevant. So basically, and this is sort of a legacy from the olden days, if you will, when this stuff was a lot, when computers, were a lot slower. But basically, when we're running some code, we want to load as little stuff and we want to do as little work as possible. So Python can do tons and tons and, thousands and thousands and thousands of different things. And if we loaded up the code to do all of them every time, it would be really, really slow. There'd just be a lot of code to run. So instead, what we do is Python itself is kind of a basic amount of code. We have all the ifs, else, fors, variables, stuff like that supported there. And we so when we have it there. And then once we want kind of more, I'll call it specialized code, we can load it from a module. So examples of modules are math, which gives us a lot of code to do kind of your non-standard math operations. Like, we have addition and subtraction built in, but if we want to do sines and cosines and stuff like that, we can use math. There's time, which is a module for things that involve timing things. There are file ones that we'll see in a little bit, but the one we're going to look at right now is random. So to get access to our module, all we have to do is say import random. So just to show you how to do this, we're going to go to the Python documentation for the random module. So you can see here, random generates pseudo-random numbers. And then right here along the side here, and I realize this is a little bit hard to digest, but it will become clear with time, is a list of all of the things that our random function can do. It can shuffle a list. It can find a random sample. but what we're looking for is random.rand int. So we want to return a random integer n such that it's in between a and b. So going back to our code here, instead of saying num to guess equals 42, we can say random.rand int, and then we can say 0 and 100. And now, just so we have debugging issues, we can say print you're trying to guess. We'll use our format again. So we can say you're trying to guess 56. 100's too high, 40's too low, 56 is right there. We won. But the next time we run the program, we're trying to guess 51. So now it's actually a guessing game. If we take this part out and don't actually tell them, tell our user, now we're actually trying to guess a random number. So I'll call 93, it's too high, 30 is too low, 50 is too low, 70 is too high. So we'll just keep trying to get there just to show 57, 58, 59, we won. So now we're actually guessing a random number. Any questions with how we use this random? So we imported it, which says, hey, load all the code we might need for generating random numbers. And then we're going to say random, which is the name of our package, dot the function we want to call. So from random, we're calling the function rand_int. And then that we're giving it these arguments, say generate a number between 0 and 100. Any questions there?
Yeah, so I've seen where you can import it as a variable name and like maybe RA, and then later on.
So we can say import random as RA, and then we can say RA.randint. What we can also do is we can say from random import randint, and then just use that function. If I can spell. So instead of having to say random.randint every time, we can say or we can just call it a name. We can even say from random import randint. Come on, this froze again. We can say import randint as. Hey, sorry, let me let my dog out. He seems to want to go outside. Apologies. Should quiet down. Great. So we can say import randint as rint, for example, if I put a space, and then we can just say rint. So we can use this as to basically retitle whatever we want. In general, and it's just a personal preference, unless I have a lot of these, I like to just import it as random and then say random.randint. Just so I know where things are coming from, and if I want to look things up, I can look it up by their real name instead of remembering what name I called it. Make sense?
Yeah.
Cool. But as you can see here, random is a very useful module. We're going to use it again later this evening, actually. We can generate random int. We can choose randomly from a list. We can shuffle a list. We can return random elements, floats. All kinds of really, really useful stuff. And just like we have random, you can see here all the Python modules. There are tons and tons and tons and tons and tons of them. If you Google it, Python probably has a module for what you need. So any other questions on this guessing game before we add one more feature, and then we're going to move on from it?
I saw a random seed function.
Yes.
Can you explain that?
Sure. So as you may have guessed here, generating random numbers is very difficult. And if I go back, actually, if we look at what this is called, it says generate pseudo-random numbers, which means, and again, the definition of this is really semantics, but we're not generating true random numbers. A computer is deterministic. It, for the same inputs, it gives us the same outputs. So these are essentially fake random numbers. So what random.seed says is we're going to reinitialize our random number generator. And what that means is if we give it the same seed, it'll generate the same random numbers every time we run it. So if we generate 10 random numbers in our program now, it'll give us 10 different ones every time we run it. But if we have set the seed at the beginning, it'll give us the same 10 numbers. Basically, it says, here is your starting point. When that might be useful, obviously not in something like this because we get the same number. When that's useful is if we're writing an algorithm, for example, that depends on randomness, but we're trying to test it and we want the same test input every time. We can use that to say, hey, we're going to like randomly shuffle these, but for now we're going to use the same randomness every time. Does that make sense?
Yes. Thank you.
Any other questions on this? Great. Cool. So what we're going to do now, before we move on, is I have this, I'll call it a quiz, but it's not really a quiz. It's sort of a Boolean practice test. So first of all, a bit of introduction. This is from a book called Learn Python the Hard Way. It is a fantastic resource for reviewing Python concepts. If we go here, and this is learnpythonthehardway.org, you can see it has a table of contents for a lot of the things that we've talked about now, or we've talked about in this class. It's a really, really, really useful review site. What we're going to do is we're actually going to practice working with Booleans and learn one or two new, learn a couple new things about Booleans and how we actually compare. So the first thing we're going to learn that's new is we have this and. So just so we can say if one thing, we can say if two things are both true, we can use the and keyword. We don't have anything else to compare here. So we'll say if this and 5 minus 7, if 5 is less than 7. So this thing is true and this thing is also true, our if statement is going to get executed. If either this, or even a third thing is false, so if any of them are false when we have an and, our whole statement here, so this whole big thing is going to be false and our code's not going to run. And just like we have and, its counterpart is or. What that says is if any one of these is true, so I don't care if you have 100 of these and just one of them is true, if any of them are true at all, we are going to execute it. So that's and or. So what we're going to do here, feel free to unmute and kind of yell these out and we'll talk about them. We're going to say...
And or are the same thing, are they?
No. So no. And is all of them have to be true, or is any one of them has to be true.
Right, okay.
So we're going to go through, there are about 20. We might not do all of them. We're going to talk about whether these statements will evaluate to true or false. So true and true. What would that be?
True.
True. The left side of the and is true. The right side of the and is true. So the whole thing is true. How about false and true?
False.
False. And all of them have to be the case. And that's not the case here. How about 1 equals 1 and 2 equals 1?
False.
False. Again, both of them have to be true, and this right one is false. Test equals test.
True.
True, exactly. 1 equals 1 or 2. So this exclamation equals is not equals. So if they're anything but true, that evaluates to false. So 1 equals 1 or
true.
False.
So it's true. So actually both of them are true. But even if this right side was false, we have the or here. So only one of our things has to be true. And 1 is equal to 1 regardless. So regardless of what the right side is, it's true. How about true and 1 equals 1?
True.
True, exactly. They're both true. False and 0 not equals 0.
False.
False. What if I made this an or in the middle? False or 0 not equals 0.
True.
True.
Nope. So this is false and this is false. So neither of them are true, so our whole thing is going to be false. True or 1 equals 1.
True.
True, exactly. We can see the first one's true and we have an or, so we don't have to go any further. Test equals testing.
False.
Yep. 1 not equals 0 and 2 equals 1.
False.
False. Exactly, they both have to be true. So the last keyword we have to worry about here is not. What not says is whatever your thing was, flip it. So if you were false, true. If you were true, false. So not, true, and false.
Can it be true?
That'd be true, exactly. So this thing, true and false itself is false, and then not false is going to give us true. And let's do one more. Let's do number 16. Not, and then 1 not equals 10, or 3 equals 4.
False.
False, exactly. So the thing in the parentheses is we're going to have true or false, which is going to be true, and then not true is false. So you can see here, these are kind of a bit tricky, but they're intuitive if you think about them. It's just the kind of thing that, practicing looking at them is really helpful. But if you take the time and, evaluate them piece by piece, they're not too tricky. Any questions on any of these here, any of the Boolean practice? So any of these, just to clarify, are valid to put in an if or else statement as is. And we can kind of run parts of code based on their truth results. Any questions here? Any of these not clear to you?
I think I need to just get my head around them. Yeah, I think it's okay.
Yeah, it's the kind of thing that, there's no tricky concepts here, but there's a lot of, words and symbols at once. So it's just practice makes perfect.
Mm-hmm.
Cool. What we're going to do now is we're going to, oops, that's the wrong one. We're going to talk a little bit about strings. We're going to go back to strings. Can someone remind me while I comment all of this code out? Well, it's going to go down here. What is a string?
Not an integer.
Not an integer, okay.
It can be anything. A string can have anything in it. It's no calculation in it or anything else. It's just it's raw output.
So it's to kind of put that a little bit more formally, but you're correct. It's a combination of characters that we want to treat as the characters themselves. So we don't care if the string says true or false or 100 or -8 or 5.3. We're just going to treat it as letters and words. So let's say my string equals
the equivalent to general in a cell in Excel spreadsheet.
Exactly. We're doing what you told us. We keep, real math on it. Great. So my string 2 is going to be 10.0. I'm going to make it a string 10.0. So just to review, we mentioned these can be in single quotes or in double quotes. Actually, let's do this over on the interactive side. Remember, so what is the result of my string plus my string 2 going to be?
10.0 plus 5.0, but it's going to output it rather than calculate it.
Right, exactly. It's just going to smush them together.
Yeah.
Cool. Does anyone remember if we wanted to actually get 15 out of this, how we would do that?
Make them integers.
Exactly. Integers or float. So we can say float my string plus.
Oh, right. Yeah, you add them. Yeah, okay.
Great. And now it gives us 15. Cool. And we also mentioned, just like we had in arrays, we can get individual characters. So my string 1 is going to give us the period. It's the character at index 1, or in kind of people language, the second character in the string. We can check if they're equal.
Is that because zero is the first, yeah?
Yes.
Yeah, okay.
So our strings, unsurprisingly, are not equal. We can say my string equals 5.0. That's true. My string equals my string, also true. Great. Let's talk about something new. So the first thing is dog, cat, horse. That's going to be our string. So we're going to say new string equals that. I want to ask, is the word cat in my string somewhere? So what I can do is I can say cat as a string in new. And that'll actually evaluate to true or false, depending on if the string, if the substring is in the string. So cat is in new, dog is in new, And since this is not an array, we can have any subset. So we can say DO is in there. We can say D is in there.
It's almost like doing a find within a string, yeah?
Exactly. It's doing a find.
Okay, cool.
Important to note, these strings are case sensitive. So while we can say dog in new is true, dog in new is false. These are case sensitive, and there's no way around that, but that's generally a good thing. There are some fun things we can do with the string. We can say new.upper is the function. It makes our whole string uppercase. And then if we have a string that has upper and lowercase, we can do .lower to make the whole thing lowercase. Go between
Can you make it title case?
Yep.
Or camel case, whatever you want to call it.
.title.
Yeah. Okay.
So we can make things upper, lower, and title case, which is often very useful if we're comparing two strings to to see if they're equal, but they might be, for example, if we're comparing words or checking if a word is in a list, it might be at the start or the end of a sentence, so it might be capitalized. So we can say just make everything lowercase and then look at it in a case insensitive way. The interesting thing that I want to look at right now is I want to look at something called split. So we're going to say my string is equal to 10, 100, 41. And what I want to do is, just like this is a CSV file, I want to get out the values 10, 141 into integers. Anyone have any ideas how I would, only using what we know so far, get those values as integers? Your hint is that it's not going to be a very pretty way at all.
Float bracket 0 or?
Yep, so we can say my string from 0 to 2 is going to give us 10. My string from 3 to 6 is going to give us 100. And then for each of those, we can say int of that whole mess, and it gives us the int. That's really, really messy. The reasoning, because if I want to get the second one, but now if I make this instead of 100, I make this 1,000, we need to change all of our things. So what we can do is we can say my string dot split, and then split takes a string, and what it does is it looks at every instance of that string and then splits into an array of substrings wherever we see one of those. So when we say my string dot split, it says wherever I see a comma, I'm going to break. So it says 1,000 is the first element, 100 is the second, and 41 is the third. So now we can make our string look like whatever we want. We can put as much garbage in there as we want. And when we split, we always get the same. We always get split at the commas. And this is going to be very, 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 very useful to us. Any questions here?
Yes.
So you'd use this in like a parsing of like a CSV file or something
Exactly.
like that?
And that's exactly where we're going next.
Oh, okay.
So I have a question here. So just by default, can you start using a regular expression to find information in there?
Yep. So the answer is, the question is about regular expressions. To those of you who might not be familiar, what a regular expression is, at least from the how to use it perspective, and we are going to chat more about those at some point in this class. It's basically a fancy way to search for or in strings. So instead of saying if dog is in our string or if cat is in our string, we can say if some pattern is in our string. So we can maybe say if a D followed by a number followed by any letter is in our string, any kind of more advanced patterns like that. And the answer is just like we have the random package, the regular expression one is called import RE. And then if you look at Python regular expressions, all of the things, and if you're familiar with regular expressions, this should be familiar. All of the things we can do with regular expressions are going to be on this page. We have find all, we have regular expression split. We're not going to chat about those now, so if you haven't seen these before, don't worry about it. But we, yes, they are fully supported.
Okay, cool. I just want to know if it was by default or if you have to import.
You do have to import it. Cool. Any other questions here?
So can you do like a regex phone number, for example?
Yes.
On a
So
CSV file, and it
a
put out
good
all the
example
phone
is so we can do a pattern like to find a phone number. So for example, at least in the US, a phone number is going to be 3 digits and then a hyphen and then 3 digits and a hyphen and then 4 digits.
Yeah.
So we can have patterns like that should pull out any phone number, even if we don't necessarily know what the digits are.
Cool. Right.
And we will get to those maybe this week, maybe next week.
Yeah.
Any other questions? Great. So now we're going to look at how to work with files. How to work with files is going to be the last real new Python thing that we do today. And then, as promised, we're going to shift gears and start looking at our data set and start playing data scientist on our data set. So Python files are really, really, really simple. You can say all you need to do to open a file. So we'll call this my file equals open. And then open takes the name of the file. So in this case, or sorry, the path to the file or just the name. So in this case.
So you do local root, do you? Or local path, yeah?
Use just been desktop and then train.csv. And I can print out my file. Thought I had the file. It's not tell the slash users, just users. Cool. So now it says open file. That's not very interesting. The interesting things we can do are file.read. And what read is it'll take my whole file and put it into one giant string, and then it's going to print it out. So that's not super, super interesting to us. The more interesting thing we're going to do is my file.readlines. And what that does is, it's a bit harder to see, but it actually, it makes a list, and then every element in the list is one line in the file. That will be a bit more clear in a second when we actually do a for loop over it. So we can say for line in my file.readline. So for every line in this array, we're going to print the line, and then let's just print a bunch of hyphens. Oops. So now we can see we have our line in our file. We print that out, and then we can print stuff on our hyphens. So now we can process each line of a file on its own. Any questions there? Relatively straightforward. The other interesting file thing we're going to do is we can say my file 2 is open, test file.text. And if we give it a W here, it will say open it for writing. So by default, we open a file to read it. And then we can just say my file 2 dot write hello world. And now we run this, and we look up testfile.text. So I have no idea where we are on my computer. Let's put this on the desktop. Now we do this and run our code, and we look on the desktop. We have testfile.text. Oops. My file 2. We need to close our file at the end. Make sure we actually write. And run this. Great. Our file says hello world. So now we've read from and written to files on our computer. Relatively straightforward. Again, relatively simple. Any questions there?
So can you now pull out stuff like we did a minute ago with so you pull it out like from a minute ago when we did it where you could pull out the commas.
Exactly. So we can say print line.split on comma, and we don't need this code anymore here. And now we actually have a list with all of the elements in our list. So now we can kind of pull them out separately. Is that what you're asking?
Yeah, that's excellent.
Cool. Then you're going to like this even better. So our another new module for us is going to be called import.
So they're like arrays now, aren't they? So
Exactly.
can we now use them as a dictionary?
That's exactly what we're going to do now.
Oh, okay.
We can say import CSV, and then we can say for line in csv.dictReader, and then we can just give this a file. And what it'll actually do is it will, so it looks, if we, as a reminder, if we look at our file, we have this header here, which is the title of our columns, and then every line. It'll actually make a dictionary for each line where the value is the value at the header. So if we print out our line here now, we can see now we have a dictionary. Name is the name, fair is the fair, et cetera, et cetera, et cetera.
I like that.
That was a lot very quickly. Any questions on that? That's going to be the last kind of new Python, I'll call it, for the night. And then we're going to move into using some of the things we just talked about in a kind of applied way on our data set. But before we do, any syntax or Python questions on any of the things we just went over?
So on that, going back to that where you were a minute ago.
Sure.
I've just copied that and run it, and it doesn't work. I'm getting an error. CSV is not defined. Is that because I've
import CSV?
Oh, okay. Yeah. Sorry. Yeah.
Yep. So in general, if you're getting something that's not defined, it generally means it's not imported. Another thing that I didn't mention is just like we have CSV and random and the regex1 and math that are built into Python, these can, as well as being built into Python, these can be files that you made. So if you have a file called my file, you can just say import my file, and then it'll actually import all of the functions there. So that's how we can break up our code across multiple different files and import just the functions that we need from those other files.
So it just makes it clean, so you can have that sort of one, and you can globally call it. Is that what you're saying?
Exactly. So just like we like to isolate logic and functions, we can isolate functions in files that do the same thing.
So if you want to, so I'll give a case scenario. So say I've got one source of information, I would put that in that my file in somewhere, yeah, and then everywhere in my project, I could then just call that at the top of the page. Is that
exactly
correct?
So
okay.
We can group together similar utilities, access information, stuff like that.
Yeah, cool.
Any other questions on this? Great. Hopefully I haven't lost too many of you, but the good news is that's all of the new Python we're going to do tonight. If you have kind of generally feeling very lost about something we just talked about or something we did last week, now some of the data science-y stuff we're going to do is going to hopefully reinforce that. In addition, we're going to bring in some data science along the way. So can someone remind me in their own words what the data science problem that we're going to be trying to solve with this Titanic data set actually is?
We're querying, just throwing this out, but we're querying the various characteristics of the people that were on the boat and the outcome of what happened to them.
Exactly. So to kind of put it into a bit more data science speak, but your general answer is exactly correct. We want to ideally use our data, but for each user in our data set, we want to predict or make a classification of whether or not we think they're going to survive. Is that clear to everybody? Okay, so last time we did this, we mentioned the first couple steps of our data science, we'll call it the pipeline. First, we have to read in our data, which we've already done here. We can read in each row and process it somehow. And then we need to clean up our data in a way that we can then start to actually use it. And then we want to start to test hypotheses about our data and start to make and evaluate our decisions based on those. So what were some ideas, if someone can remind me, what were some of the ideas you guys had last time about how we can actually go about making these predictions. I remember we talked about age, we talked about sex, we talked about fair, stuff like that. Can someone throw one of those out there?
Age lower than 18, probably gonna survive. Age higher than 18, probably gonna die.
Great, perfect. So what I want to do is I want to write a function called predict. Def predict. Predict is going to take, it's going to take a whole row. We're going to call it data point. So I'll just put a note here. Predict takes a data point and predicts whether spell person will survive. Cool. So we mentioned here, first idea, over 18, no. Under 18, yes. Cool. So we have here a column called age. So we're going to say age is going to be data point, which is a dictionary. So we're going to get the key called age. And then we can see here that it's a string. So we're going to say, we're going to make this an int. And now we can say if age is 18, return, or it's over 18, return false, else, which means under 18, return true. Is that clear to everybody what we did here? We got the age out, we made it an int, and then we're returning either true or false based on that. So now for every line, in addition to printing the line, we can print out, we can call our predict function on our line, and it'll print out a prediction. So scrolling up here for a second, we're going to ignore that error. We'll come back to it in 1 second. This passenger is 22, so we say false. They didn't survive. Also false, also false. So all of these passengers were over the age of 18, so we say none of them survived. But hey, wait a second, we got an error here. It says invalid literal for int with base 10, which means we couldn't get an int. And if we look at our row, we see that age is unfortunately the empty string here. So any suggestions about what we can do here? And we don't have the age. So as I mentioned last time, cleaning our data is going to be the most boring, but probably most important part of this whole project. So we need to fill in something or do something with these data points that don't have an age. Any suggestions?
You're gonna have to do a try catch for missing spots.
That's an option. We're actually not going to talk about try catches today, so I might skip that option. But the option there is basically if a row doesn't have an age, we have to skip. We want to skip it. That's a very valid option. The reason I don't like that option is because someone giving us a data set is likely going to say, hey, I want a prediction on this whole data set. If they ask for 100 predictions and we go, well, I can only give you 58, they're probably not going to be very happy. So what I want to do instead is I want to fill in a value for age itself so we can actually make a prediction for that row. Any suggestions about what value would make sense to fill in?
You could take an average of the ages and fill in the missing spot.
Exactly. I like that idea a lot. So what we're going to say is before we do any of this prediction stuff, we're going to go through the file.
I didn't hear his the last part of what he said.
The suggestion was to take the average and then fill that in.
Oh, fill that in. Thanks.
Yep. So for line in our file, we're going to read the file in again. And we're going to say if line age is not equal to an empty string, which means we have an age. We'll call this ages. We'll make a list. We'll say ages dot append, and we're going to actually append an int of the age. So if I comment all this junk out for 1 second and print ages, we're gonna all right, well, we see another problem. We see that some of our ages are actually floats. That's an easy one to change. We're going to go right here and right here, and just make them floats. So again, this is just playing with and getting to know our data. So here's a list of all of the ages that we have. Just like I promised you guys last week, once we once we've written the hard way to do something, like find the average, I get to show you guys the easy way. So we can import a module called NumPy. Some people call it NumP. Basically the same. So we can say numpy.mean of our ages. And now what this is going to be is it's going to print out, it's going to say our average age is about 29.7. So again, NumPy is just it's actually a third-party one, but it's just a Python module that has a bunch of numerical functions. Another one that we will chat about at some point, maybe today, maybe not, is standard deviation. But a lot of really useful mathematical functions are within NumPy. So what we can say is average is equal to the mean of that. And now we can uncomment all this code out, and we can say, if line age is not equal to the empty quote, so if we have an age, we're going to set our age to the float of the age, else age equals average. Is that clear to everyone what we're doing here? We could say, all right, we calculate the average, and now if we can get the real age, get the real age, otherwise set it to the average. And now our whole program runs without errors. Anyone who is over 18 passes away. Anyone, find one here, this person is 15. Anyone who is 15 survives. Cool. Any questions? So what did we learn about our data here? Anything? Anybody? Did we learn anything about our data here? If the answer is yes, what did we learn? If the answer is no, why not?
I mean, it needed to be cleaned and so.
Sure. So we learned a bit about kind of we'll call it the shape and types of our data. But what I'm more asking about is, again, we're trying to make not just predictions, but we're trying to make data-driven predictions. So did we learn anything about, if our hypothesis of being over 18 or under 18 was correct?
No, we didn't, because we didn't compare the results.
Exactly. So we want to compare now to the truth value, and we can start to evaluate how our predictions went. So let's write a little bit more code for that. So we now have this variable. We'll make it into a variable. Prediction is equal to predictor line. So now is true or false. And now we want to compare that to the truth. So the truth here is survived. So we can say if, we'll call it survived is line. So we're going to get this variable from our line. And now we can say, now we want to make, so this is going to be a 0 or a 1. So it's going to be 0 or 1 from the line. 0 means they did not survive. 1 means they survived. So we want to make this a Boolean, and then we want to compare it to the our prediction. So we'll call this survived bool. So we can say if survived is 0, survived bool is going to be false, else survived bool is going to be true. And now, instead of printing our prediction, we can print prediction equals, double equals here, survived boolean. And now we print these out. We can print out true or false, depending on whether or not we were correct in our prediction. Helpful, not helpful, and if it's helpful, why? If it's not helpful, why not?
It's not helpful because you need to look each one of these to know if it's true or not. So you have to count each one that is true, To make
Exactly.
a percentage.
So, exactly. So we're going to get a percentage. We're going to call this results, and we're going to make a list. And now, instead of just printing it out, we're going to say results dot append this value. And now at the very end, once we run all of them, we can say print results, and now we'll learn a new thing dot count, which is how many of something there are. We're going to print the count of the true, and we're going to print the count of false. And now when we run our code, we have 550 times we were correct and 341 times when we were not correct. So if we do some 550 divided by 550 plus 341, we are 61% accurate in our prediction. So now what have we learned?
That you can kind of trust in a hypothesis.
Okay, why do you say that?
You can't rely only in one variable, and it's not that reliable because 6% is not a higher number.
Okay, so those are good points. We can't really rely on one variable. That's throwing out a lot of our data. The other point is 61%. You know, it's good, but it's not great. We're certainly not going to shatter any records with that. There's a comment in the chat saying age isn't enough, which is also correct. What I will claim, and I want someone to explain why I'm claiming this, is 61% is way worse than it seems. Why am I very unhappy with 61%?
Failing.
It's failing, yeah. It's a D minus, not great. What's a more data set specific reason why I might not be happy with 61%? So the reason, and this is your, if you only take one data science thing away from our lesson tonight, is that we don't have what's called a baseline. When I say the word baseline, what comes to mind?
Like a standard normal.
Exactly, something to compare to.
A benchmark.
Yeah, exactly. A benchmark's the perfect word for it. We need some kind of benchmark. And the reason for this is, let me just go through our data set right here. I'm just going to do this really quickly just for the sake of getting numbers. We'll call this truth, if I can type, THS is going to be a list. And all I'm going to do is say truth.append line through. We'll do the Boolean. And now instead of printing out the result, whether or not we're true or false, I'm just going to print out, and I'm going to make this so that we print out the accuracy. So I'm just going to divide the two. So we'll call this correct is that. Wrongs is going to be the count of false. And then we're going to print out correct divided by a float of corrects plus wrongs. So when I print this out for, first what I'll do is I'll do this for results just to show us, make sure it's still 61%. Cool. So when I print out for our results, it's 61%. But what if I just look at the correct answer? So the correct answer here, if we say, we look at it and we say only 38% of the passengers survived. So if we say 38% survived, 100 minus 38 here, it's going to give us 62, which means 62% of our passengers died. Can someone maybe have an idea of why, while knowing that number, that makes me very unhappy with our prediction? Any guesses? So if we know that 62% of our passengers died, what if our prediction function just said, I don't care how old you are, I don't care what sex you are, I don't care how much fare you paid, I'm just going to say you died. We would get 62% accuracy, wouldn't we? Right? If we say, so what I was saying is our prediction from accuracy percentage is just as good as not even looking at the data point and just saying every passenger died. Is that clear why that's not good? Or why it's sort of a red flag?
It's too broad.
It's too broad, exactly. So what we want to be able to do now that we have a baseline, we can say, hey, 62% is our baseline. If we don't even look at the data, we can get a 62%. That's like saying, if I don't even write in a single answer on my test, I get a 62%. Well, if you filled in that test questions and then still got a 62 or got a 63, you'd say, well, I really didn't do that great. Does that make sense? So what a baseline does is it says, hey, let's get a benchmark for this problem. And then let's get a really simple one so that I can see if I'm doing better. So 62% on this one is kind of a lousy result because, hey, our baseline is 62%. But let's say we're solving a really hard problem, like figuring out what an image, which of 1,000 categories an image is of. Well, if I can get 62% on something that's 1 in 1,000 choice, I feel really, really good about that. That's probably, maybe not a world record answer, but very impressive progress. But here, when just by picking yes or picking no and not even looking at our data, we can get a 62%, well, that's probably not too, we probably want to improve our methodology. Does that make sense to everybody?
Yeah.
Cool. So now that I've downplayed our solution a little bit, let's actually improve it. So I'm going to,
Ben, I have a question.
Sure.
Isn't using the average age skewing our data? I mean, especially if there's a large variance in ages among the passengers. And I mean, you could argue that having an incomplete record in itself is a data point, no? Exactly.
So yes, it's absolutely something we're going to get to, but to jump the gun a little bit, we went with average. That's a kind of a very common one to fill it in. What's often done is, as you mentioned, filling in something totally different and, deriving meaning from the fact that we don't have a data point. We're going to get to that at some point tonight. If I happen to forget, please bring it up before we end, but that is something we're going to chat about.
Okay, thanks.
Cool. Can anyone think of any suggestion? I'm just going to run this to make sure we still get our 61%. Can anyone think of a suggestion to improve our methodology here? How can we make our 61% better?
I'm sorry, Ben, would you mind scrolling on the console?
Scrolling what?
On the right console, yep. I'm not seeing it update or change.
The 61
right
the bottom
there.
Here.
Okay.
So I want to try and make our model do better. How can I do that?
We need to use more variables.
Yes, we can use more variables. I want to only use age. I maintain that we can use only age and do much better. Any guesses? And we will obviously go and use the rest of the variables. But for the next few minutes, I want to focus on only age and kind of getting the most bang for our buck using that.
You can try to look at the different tests because you are only saying that below 18 and higher than 18 is going to not survive. So if you put a different interval, maybe you're going to do better.
Cool. I like that idea. Let's change it to 20.
And couldn't you use more than 2 intervals?
Exactly. So
like very young kids probably won't survive in the cold. So less than 5 don't survive. Between 5.
Exactly. Cool. So I like these ideas a lot. So we're going to revamp this. We're going to say, and I'm just going to make up some numbers here. We're going to say if age is greater than 14, we're going to return false. Else if age is, let's say, people older than 65 probably won't survive, return false. And if you're in between 14 and 65, we think you're probably good. That didn't do very well for us. We can see our number drop down to 37.5%. But I really like the idea of using using a range. But it didn't really work here. And it seems like we're kind of taking a lot of stabs in the dark at solving our problem. So can anyone think of a better way to do this than kind of guessing ranges here?
Can we build a histogram?
Yes, perfect. I like
like
that answer a lot. So to do this, we're going to need a little bit of new code. So what I want to do instead of a histogram, we're going to do a histogram second, is I want to look at our data. So instead of saying ages, we're going to say ages survived. Actually, I'm going to comment this out because we will still need it. So we're going to say ages survived and ages died. And now, instead of just saying this, we can say if line. So if the person did survive, we want to add this to the list of survived ages. And then else, if they didn't survive, we want to add this to the list of ages of people who died. Now we can print it out and say print ages survived, print the mean of ages survived, or I'll just print it. We don't need to set it to a variable. Ages died. And we can comment all this stuff out for right now. And now we run this code. So all I changed was instead of just reading in every age to the same list, we're going to read it into two separate lists. And now we can say the average age of a surviving passenger is 28. And the average age of a passenger who didn't survive is 30. So this is kind of the first, it's an important step. It might be subtle, but it's the first time we have used, used actual information derived from our data and statistics derived from our data to make a prediction. So I want to modify this a little bit. We're going to go back to ages, just back to one list. But what I'm going to do here is I'm going to make a parallel list called survived. And here I'm going to print survived.append true and survived.append false. So just to show you what I've done here, I'm going to print ages and I'm going to print survived. So here we have a list of ages, and then for each one of these ages, we have a corresponding element in this list, true or false, whether or not a person of that age survived. Is that clear to everyone what I did here?
Yes.
Cool. So what I'm going to do now is I'm going to import a new module called matplotlib.
Can you concatenate the lists? How do you do that again?
Yes, we could. As PLT. So we have this package called pyplot, and we're just going to call it PLT just to type it a little bit easier. What we can do now is I can say plt.scatter, and this is going to make us a scatter plot from our two lists. So I'm just going to make these, instead of true and false, I'm going to make them 1 and 0. And print that. So this isn't necessarily very helpful right now, but we have a scatter plot where these are the ages of all of our people who did not survive. And up here, we have all of the ages, all the people who did survive. So now we can actually visually start to look at our data and start to, play around with saying, what does the data look like? So what does it look like from what do we see in the scatter plot? Does anyone have any observations about it?
Heavier between 20 and 40.
Exactly. So definitely a lot of people between 20 and 40 in both. How about up here? So it looks like there's kind of one person up here, but it looks like, once we get this 65 cutoff, the people are much, much, much more likely to not survive. Does everyone see that? See why I say that?
Yes. Is there a way to get the exact point where this break starts?
Yes, and we're going to chat about that. We'll come back to that. So what this lets us do, though, is it lets us start to kind of make decisions from our data about where we can put these thresholds. Does everyone see why that's really important? That why drawing decisions from our data is preferable to just kind of making things up and guessing?
Yes.
Cool. Any questions on this scatter plot code's a bit confusing. We're going to have pretty much a whole lesson on how we actually make these visualizations. So if it's not totally clear, I guarantee it will be drilled into your brains by the end of that.
So is this quite good for, like, say I'm doing Google AdWords and I want to plot my data out? Is this quite good for that? Or?
Yep. We're going to talk about all different ways to, again, to plot our data in ways that we can draw, not just decisions, but data-informed decisions from it.
Mm-hmm.
Cool. So what I want to also look at is, so what I want to do now is I want to bring a second variable into play. And then we're going to build our classifier, which is really what we've done in this predict function, based on two variables. So I want to have age, and I also want to have gender, and I want to make a prediction based on not just age now, but age and gender. So what I want to do first is we'll call it genders is a list. And then we'll say, so the first thing we want to do is we're just going to write this code, and we're going to assume, so let's put an and here, because we can't assume every line has the gender field, just like it doesn't have the age field. So if line gender.
Can I ask something really quick?
Yes.
Since you're starting to analyze another data, that means you cannot improve anymore after visualization of the data?
Nope, not at all. We're definitely going to come back. What I want to do is this visualization is a bit crowded. So by adding another data point, the visualization is just going to become a little bit less crowded so we can start to see more. But we're definitely not done with getting stuff from that variable. We're going to keep coming back to it.
Okay, thank you.
Yep. So if our gender is not none, we can say genders dot append. We can't say it's float, so we'll say if line gender equals, and I think it's male with a capital M, but I'll check. Nope, it's lowercase. And it's called line sex, not gender. So if it's male, sexes dot append a 1, else sexes dot append a 0, and we're just gonna move this code down here also. So now instead of plotting age and their survival, we're going to make a scatter plot of age and sex. But that's not very helpful, is it? We have it here, but we don't now know whether or not they survived. So we can do something really cool. And instead of making us survived 1s and 0s, we're going to make it green, G and R, which are going to stand for green and red. And again, don't worry about how these visualizations are being made quite yet, because we're going to chat about them in morbid, gruesome detail. But we can say colors equals survived. Color, sorry. Now we get this really interesting one. Now we can see on the x-axis is someone's age. On the y-axis is their sex, 1 being male, 0 being female, and then the color being whether or not they survived. So now what do we see? What conclusion comes from this?
Sex is a more important predictor than age.
Very. Or at least it appears that way. So we can see here at the 0, females, I see a whole lot more green than red, and males, I see a whole lot more red than green. Even more specifically, I see a lot of green in this top left corner. It looks like kind of below that 18 threshold for males below 18. And then I see females between maybe 18 and 65 are a very good chance to survive. And then anybody above the chance of 65 has a small chance of surviving. Is it clear to everyone how I'm drawing those decisions from this data?
Yes.
Cool. So now let's actually take that information that we've learned and write it into our prediction function. So we'll call it, if we have line age, we're going to do that. And now we're going to say if line sex not equals the empty quotes. So now we can say if it's male, we'll say male equals true, else male equals false. So now we have this variable. We have two varies. Age is the age. Male is a Boolean if the passenger male. So now let's actually code our logic. So we can say if age is less than 18 and so let's not put an and, let's nest it so we can show we can do that. So if age is less than 18, now we can say if male equals true. So that's going to cover this top left where say under 18 males, we want to return true. It's going to say, hey, you probably survive. Now we can say else, or to make it clear, we can say elif male not equals true, or the same thing as male equals false, return false. Now we can say elif, so now let's cover the above 65 age. Age is less than 65, or greater than 65, return false. We're going to say if they're above 65, we're going to return false. And now we're going to cover the else, which means that in between 18 and 65, we can say if male return false, which is going to be this big chunk in the middle. You'll notice here I left off the equals true. If you're just checking if something is true or false, that's optional. So if male is the same thing as if male equals true. And then else return true. So you can see here we fully coded up our logic. We're saying this area of the graph right here is going to be true. This area right here is also going to be true. Everything else, so males above 18 and females below 18 are going to be false. And now I'm going to uncomment all of this code and see if our accuracy actually improved. And if you look at that, we jump up to about 75% accuracy. Any questions on any of that? It was a lot of code very quickly. Scroll over here to see if we have any questions. Nope. Cool. So can someone explain to me
Will we get this file later, Ben?
What'd you say?
Will we get this file later so that we can go over it again?
Yes.
Yeah.
As usual, you will get the whole file. Cool. So can anyone explain to me in their own words, why I'm happier with this result? And there are multiple reasons, so there are a bunch of right answers here, but I am much happier with the 75% than I was with the 61%, both in terms of, the actual number being higher, as well as the process, I'll say, was better. So can someone explain to me why in their own words, especially the process part, why I'm happier with this process than the other one?
Because you've used more data points to get to that figure.
Exactly. So in addition to using more, I'm going to introduce a new word, I'll call them features. So you can think of a feature, at least for now, as just a column. So instead of using just age, I've used age and sex. So we're using more information about our data, which is great. Why else might I be happier now? Anybody? So the reason I'm much happier now is because I didn't make up an algorithm I didn't make up the prediction. Before we said, hey, I have this idea that people over 18 survive more. And, looking at this data, that, might not actually be true. But now we've actually not only kind of come up with an idea and verified it, we've started to draw assumptions from the data itself. So we've started to say, hey, look, the data is telling us, here's your answer. And we started to use that in our prediction. Instead of saying, hey, I think this is true, let's test out, let's test out if this is, if this appears to be the case. Is that clear?
Yeah.
Okay.
I have a
Now,
question.
Yes.
So at what point would it be considered to be like overfitting to the data that you have with the data set?
We will get there next week in much more detail. So the question was about a term called overfitting. And this actually is as good a time as any to talk about it. So I'll talk a little bit about it now, what that word actually means, because it's a word that you'll hear a lot. So what overfitting means, and anytime you're kind of doing data science, people will be concerned about overfitting. What overfitting means is you learn too much about your data, like your specific data, and not enough about patterns in your data, in the data at large. So when we're doing the data science problem, in the vast majority of the cases, we don't have the I'll call it the complete world view of information. In fact, what we're trying to do is we have a limited amount of data, and we are trying to extrapolate patterns about how this data actually behaves from the data itself. So an example is, we have this data from the Titanic, and we're trying to learn about who survives and who dies in a shipwreck. What we could then do with this model is try and extrapolate from it and say, make a prediction for another shipwreck, stuff we haven't seen before. So the question is, with overfitting is, are we sure we're learning about data about shipwrecks, not about the specific passengers? And to make this clear, we can look at another example. Let's say we're looking at pictures of cats and pictures of dogs. But the only pictures of cats you have are of your friend's cat, and the only pictures of dogs you have are of your dog. So you might learn that the number of legs they have doesn't really matter, but you happen to notice. So let's say we can look at something like tongue length. We can say, hey, look, dogs' tongues are longer than cats' tongues, or we can look at the height of the animal and say dogs are bigger than cats. So the bigger it is, the more likely it is to be a dog, which sounds really great. That probably holds true. Obviously there are some dogs that are smaller than cats, but in general, saying the bigger it is, the more likely it is to be a dog is a pretty good prediction about, I'll call it the world. The average dog in the world is larger than the average cat. So that's the kind of stuff we want to learn. On the other hand, let's say your dog is brown and your friend's cat is black. So you can say if something's brown, it's probably a dog. If it's black, it's probably a cat. Well, that there are tons, there are brown cats just like there are black dogs. So the color doesn't necessarily matter quite as much. That's an instance of learning something that just happens to be a pattern in our data set. So in this example, in the Titanic example, what we can start, an example of overfitting, we can say if someone is 78, they survive. If someone's 76, they die. If they're 74 or 75, they survive. If they're 73, they die. It's probably very clear to you, on an understanding level, why that's probably not an accurate prediction. Even if it's accurate on our data set, chances are, there's going to be some variance in all of these age ranges. Not everyone in every range is always going to be correct. So overfitting is when we're finding like very, 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 very specific boundaries in our data set, and then making assumptions about the world based on stuff that's really just random noise in our data set. So in this case here, we've only drawn a few boundaries. We've drawn basically 3 of them. We've drawn 2 age boundaries and a gender boundary. So we're still making very broad assumptions and very broad boundaries. Overfitting is when we get to the point where we're making very, very, very specific and fine-grained assumptions. And that's often a problem because it's kind of explaining noise instead of actually explaining patterns. Is that clear to everybody what kind of the distinction is there?
Yeah, so it would be like if we were to say that one person who was 80 years old, we had something in there saying
Exactly. So if we, put another thing here, elif age is greater than 78, return true. So we went from 74.9 to that person must not be older than 78. We'll call him 74. Hey, look, our accuracy went up to 7.749 from 0.741. Our model must have gotten better. But in reality, that's probably not a real, probably not a real thing we have to worry about. It's just kind of a very specific quirk in our data set. So that's not the kind of stuff we want to look for. We want to look for the very broad, very generalizable things. Does that make sense?
Yeah, so would you be going for like a range of accuracy that you would say is acceptable, like between 70 and 80?
For a range of accuracy? What do you mean by that?
Like how you have 0.75 right now. Like
Yep.
When would you know it's time to stop? All right, I'm good right now.
So just like we want to have a baseline for a problem, which kind of tells us if we're doing better than, we'll call it a dumb solution. With every problem, it's also important to have a goal with kind of what's within the realm of possibility. So for example, in the Titanic, as we can see here, we're never going to be perfect, at least with these two variables. So, there's no way to chop this up other than in very, very, very fine-grained overfitting ways that's going to be perfect. So it was going to be wrong somehow. But we can kind of see that, let's make a decision saying, hey, if we hit 90% on this problem, we're probably doing pretty darn well. That said, there are a lot of other problems where 90% is kind of, a joke. So for example, all of you, I'm sure, have an email address, and all of those email addresses have a spam filter. If 90% of the emails you got were wrongly classified as spam or not spam, you'd be pretty pissed and you get a new email provider, right? But on the other hand, there are incredibly difficult problems that, even getting 50% on something is a huge accomplishment. For example, in a lot of like medical practices, like doing image recognition stuff, if you could, with 50% accuracy, tell me exactly what's in an image, you'd be very, very rich and on, very highly, have offers from Google, Facebook, and everyone. So there are certain problems where you have, 50% is a great result, and there are certain problems where 90% is a terrible result and less than your baseline. So the answer is it really, really depends on your problem. And the only way to know that is kind of to get a feel and say, hey, here's what my baseline is. Here's how we think we can improve on that. And, here's what looks like possible to get from the data without overfitting. Is that a good answer for you?
Excellent.
Cool. Any other questions about this and, the stuff we've done so far before we move on a little bit? Check the chat. No questions?
No, all good.
Great. So what I want to do now, we've got about 25 minutes left. I want to spend maybe another 10 or 15 minutes improving both our solution to this problem and what we've learned from it. And then I want to spend the last 5 or 10 minutes chatting about how we move forward, things to do between now and next week, and kind of where we're going to be going with this problem. But before we get there, let's talk about improving our solution. So I want to gain another few percentage points before we stop chatting. How can we make our solution better? Who has an idea?
How about if we look at how much they paid for their tickets?
Sure. I'm just going to plot. So we decided here that, and I'll comment all of this out meanwhile, we decided here that their sex was much more important than how much, or than the age. So let's look at, instead of age, let's look at fair. So if the line fair is not going to be none, age is, we're just going to, every time we see age, we're just going to replace it with fair. And then ages is going to become fairs. I'm going to do a whole lot of copy pasting really quickly. Cool. Let's make this scatter plot.
Oh, but question about that. It looks like the numbers really vary. Is it because that person paid for multiple people, or?
Nope. This is for their own fare.
Okay.
Cool. So on the x-axis here, we have fare. And on the y-axis, we still have gender. So it looks like what we thought before was true. It looks like our females are still surviving at a higher rate than our males, but we see something very interesting on the x-axis. What do we see on the x-axis?
It's pretty equal.
Well, to me, it looks like, especially in this range over here, it looks like the more someone paid, the more likely they are to survive. We have all of these ones over here, people who paid a lot, they appear to survive. To make this a bit clear, and we're going to explain why I'm doing this in a second, I'm going to add another little if statement here. So if we have a fare, I'm only going to take a look at it if it's below 100. So we're basically, if you can see my mouse, we're only going to look at this section of our data here. So now does that become a little bit more clear that it looks like there's a whole lot of greens over here and there's still not too many greens over there. So what I'm going to hypothesize is the more someone paid for their fare, the better their room was, and maybe the closer to the top deck it was, and the more likely they were to survive. Does everybody buy that?
But it seems like the cluster is closer to the lower end of like like between 0 and 40, or like maybe like 5 and 40.
Yeah, there does appear to be a big cluster here. I was kind of more looking up here. So what I'm going to say is, and just as you agree with me, we can't come to a conclusion, at least based on this. We'll come to a conclusion eventually. We cannot come to a conclusion based on this about an answer for fare. So I'm going to call it not very useful for right now. What I want to do is, instead of looking at fare, we have this thing called class, which is basically the ticket class. So instead of saying how much you paid, how good of a deal did you got, are you first class, second class, or third class? So we'll call this classes. Instead of fares, we're going to do classes. Class.
There is no hotkey to substitute, replace all that.
What did you say?
Is that a hotkey to replace all that?
There is. I don't know it off the top of my head. So it's P class. Sorry, P class.
Yeah, P class.
So now let's see if this tells us anything. Well, we don't have we don't have too much because all the data points are basically on top of each other. But we do have this looking very interesting. We have passenger class 1. There's a whole lot of greens. And again, this is only, so first of all, do we understand why there are only 6 data points here?
Yeah, 2 genders and 3 classes.
Yep, exactly. So there are 2 genders and 3 classes. So again, it looks like, so the color it's showing is the majority at that spot. So we can see the majority of people in class 1 survived. Females in class 2 survived more than not, and then everyone else died. So it looks like, at least from this very, very limited scatter plot, and next week we're going to start off by talking about better ways to kind of view more information here. It looks like from this very limited scatter plot that people in a higher class ticket survive more often. And again, semantically, that makes a lot of sense because it seems like a higher, the higher class you are, the closer to the top deck you are, the easier it is to get out. Does that make sense to everybody?
Mm-hmm.
Cool. So what we're going to do here is now let us put this into our model. So now before all of this stuff, we can say if line P class is a 1, return true. So before we don't care about anything else, we care about your passenger class, and that is it. So let's see how that affects our answer. Oh, we went down. So it looks like we have to care about more than, we might have to incorporate passenger class into, into our other if statements. But I don't want to do that. And the reason I don't want to do that is because this is kind of growing out of hand. So if I asked each of you, and I don't know the number off the top of my head how many of you are on this call, but if I asked each of you where to incorporate passenger class into our kind of nested if statements already, I bet you would each have a very different answer of how we went about doing it. So my question is, and this is going to lead us into the discussion of how we improve things next week, is how can I integrate a new variable without having to make any decisions about it? So any suggestions there about how we, what am I talking about here? Why would I want to, what do you mean not knowing anything about it? I want to be able to incorporate it into our decision process without having to make this if statement tree grow indefinitely. Because, if I go to add a fourth and fifth and, seventh and 12th variable, that's going to get very, very, very messy very, very, very quickly. So what's next? Where do I go from here in a way that we can integrate new data without knowing stuff about it? Who has a suggestion? Somebody has to have a suggestion.
Can you iterate through them and check them?
We can iterate through a bunch of variables and check them, but we still have to make some kind of decision about it.
Can you use regression?
Exactly. So regression is a bit, that is a specific instance, but the answer is we're going to introduce our magic buzzword is machine learning. Instead of us saying, here's what to do, we're going to say, hey, computer, learn the best decisions to make. So when I say machine learning, let's spend the rest of our time, or at least the next few minutes, let's define that word. What is machine learning? Who wants to throw out a definition?
So it's like training the data by having some true set that you show, that you sort of teach the algorithm with, and then you run it on the broader part of it.
Exactly. So we have this idea of training. And what the training in this case means is here when we make a decision, we can see when we write our predict function, we have to teach the computer how to make the decision. We say, if this variable is greater than this, do that. If this variable is a 7, do that. If the passenger is male, do that. If they're class 2, do this. And we have to give it the procedure. What machine learning will do for us is say, instead of giving it the procedure for how to make the decision, we give it a procedure for how to learn a decision. And we say, I don't want to have to tell you that the cutoff is 18 and 65. I want to tell you to make a cutoff in age, and you learn what the best cutoff is. And you learn what it means to be class 1 versus class 3. So that we can just give you new variables, and you can start to learn what to do with them and make the decisions for yourself. So we add new variables, the computer will know what to do with them and automatically draw those lines. So instead of giving the specific steps to do something, we guide the computer to learn the steps, how to actually go ahead and do something. Does that make sense?
Yes, it makes sense. But what does machine learning return back? Does it return a regression, a formula, an algorithm? What?
So it depends. There's going to be a bunch of machine learning algorithms. We're going to spend probably at least an hour next week comparing and contrasting a bunch of the really popular ones. What we're going to think of it now is machine learning is a two-step black box. First, we give it all of the data we have at once and say, hey, learn how to make a decision. From there, we can say, hey, given a data point, make a decision for us. We're going to talk about kind of how both of those steps work next week. But what machine learning is going to give back is it's going to essentially give us back a predict function. And we'll talk about how under the hood it makes the predictions. But what it's going to do is say, hey, given everything I've learned, I'm going to give you a prediction. So instead of us having to write all this code, we can just say, give us a prediction, learn how to make the prediction instead of us telling it to you. Does that make sense?
Yeah, it makes sense. So it's a black box, like you said.
It's a black box for now. We're going to spend next week dissecting the black box and, making it less so and talking about what actually happens.
Okay, yeah, it's pretty clear.
So I have
Cool.
a question here. So it's like these algorithms, they're going to just go through all the variables and try to find the right or the ones that are most likely to survive. And it's going to give us some sort of like parameter that we could then use.
Exactly. So let me perhaps find an image. Jump the gun a little bit. Linear regression, get an image.
So
Cool.
my question for that is like, we were looking at that data and we have an idea what age means and what sex means and, capabilities for those variables that perhaps the computer wouldn't really know.
Mm-hmm. I'll get to that in 1 second. Let me show this example. So the example here is, and this scatter plot should look just like the ones we were looking at. We have some variable, we don't know what, we don't care what on the x-axis, and we have some other variable we don't know, we don't care about on the y-axis. And then we have, we'll call it red and blue are survived and died. Well, what we would do here, once we plot this, is we would try and figure out how, write code to make this decision. What the computer or what machine learning will do for us here, in this case, is it's going to say, hey, I'm going to learn that this line is the best possible decision we can possibly make. Anything above this line on the graph, we're going to say is survive, it's blue. Anything below this line on the graph, we're going to say red. So instead of us specifying to the computer where to draw this line, the computer is going to actually learn for itself the optimal place to draw that line. So instead of us having to specify under 18 or above 65, the computer is going to learn where to draw those lines for us. Does that make sense?
Yeah.
For now.
No, go on.
Just saying, it makes sense for now. I need to digest it more.
Yep, we're definitely going to talk about how this actually happens and what actually happens and, mathematically what's going on here. But the way to think about it right now is if we, if I told you to draw a line between red and blue here, you'd have to think about how we actually do that. The machine learning is going to let this computer draw the line for us.
So like even
spot.
So you have X amount of people who are asked that same question. Where would you draw that line? The computer has a suggestion on where you draw that line.
Yep.
How do they?
So basically what a machine learning algorithm does is, given some set of constraints, and we'll talk about the comparing and contrasting the algorithms based on the set of constraints we give it, it's going to find the best possible line. So this line here is actually the line, and you can mathematically prove it, that best separates red and blue. So it's a single line that has the most reds below it and the fewest on top, and the most blues on top and the fewest blues below it. And you cannot possibly draw a better line than this on this data set. So the computer is actually going to give us the best possible answer for this problem. Sounds great, right?
Yeah. Is that
Now,
line then? What is that line in the graph? Like, what are those dimensions? Is it more or less like a n-dimensional line because it's taking all the different...
We're just going to look at it in 2 for right now because it's what we can see. But you can, if you want to think of it in 3 or 5 or whatever, you can't do that visually. But it's really the same thing. We're just kind of making separations in a graph.
Okay.
So this sounds great. This sounds like magic. Seems like it to me still too. There are a lot of problems with this and, trickiness, which is where we're going to pick up next week. But for right now, we can think of this as the absolute best possible line between these two. And, you could test it out. You could write something that draw a line. It tells you, your accuracy, and you're not going to get one better than this. Any questions? This was kind of a lot of both Python syntax stuff as well as a lot of conceptual stuff.
At the moment, we're importing CSV. If we wanted to import, say, XML, JSON, or another data format, what are the other data formats you can do? Is it anything? Or?
XML and JSON are the big ones.
Yeah, text files as well, maybe?
Yep, this text files you can just open up with file.
Yeah.
CSV actually supports TSVs separated by tabs also. And then there's plenty of stuff. We're not going to cover it, but there's lots of stuff to talk to databases and all that too.
Cool.
Any questions on this, on what machine learning is, on what we're going to do next week? Hopefully that became a little bit more clear on anything we've done in the data set, of anything we've learned about our data set. I'm going to kind of draw the line in the sand here and say, if you have no questions and want to head out, we are not going to cover anything new for the remainder of this lesson. I'm going to hang around for 10 or 15 more minutes, or as long as you have questions to answer any of them. If you have no more questions, I'll be posting all of our code on the Slack channel again, like I did last week. And I will talk to you next week unless you have questions for me in between. Thank you guys for coming. So now I will stay around if any of you have any further questions.
Yes, Ben, you mentioned you were going to talk some more about missing data points and how...
Right. Thank you. So missing data points, a very common thing to do, and there are multiple different ways of filling them in. I didn't want to not make a prediction now for what we were doing before. They are often left out of the training set. We'll talk about what exactly the training set is next week, but skipping them is a valid option. Just like we replace them with the mean, replacing things with the median is very common. But I think what you were hinting at is replacing them with a separate value, saying, hey, we don't know. There's something important in that. And that's absolutely the case. So let's say instead of replacing age with the number, we replace it with 500. And then we have a special case for if age is 500, let's look at that separately. So yes, that's very, very common, replacing with a special variable, or with a special value rather, and that can lead us to some very good results too. So there are tons and tons of different ways to deal with missing data. The other thing is when we were looking at FAIR, there were a couple of FAIRs that were very clear outliers. Just like we have to deal with missing data sometimes, we very often have to deal with outliers and just data that doesn't make sense, and we have similar techniques of dealing with them. We're going to talk more about outliers probably the fourth lecture. But there are, that's kind of a lecture in itself, potentially, of what to do with missing, incomplete, and potentially wrong data. But the short answer is you can do anything you want with it. If it improves the model, it's probably correct.
Okay, thank you very much.
Yep. Anybody else?
Just kind of in general with machine learning stuff, is there any types of data sets that aren't really well suited for the different types of machine learning, or?
Yep. When we talk about different machine learning algorithms, we're going to talk about their strengths and weaknesses compared to each other, as well as what kinds of data sets they tend to work well on. So stay tuned for next week.
Okay, cool.
Ben, how would that line look like in your problem?
Can you say that one more time?
How would that line look like in your problem?
Oh, that's a bit of a, I'm going to save that for starting off next week. Basically, in what we did here is instead of drawing a straight line, we just kind of blocked off chunks. So if you think about it, we were kind of taking quadrants. So instead, we didn't actually draw a line quite yet for our problem. What we did was we talked about quadrants of the graph. So we said maybe from 0 to, from 0 to 2 on the x-axis and 0 to 4 on the y-axis, that kind of square, that's going to be survived. And this square is going to be false. So our algorithm is actually not advanced enough to kind of draw a line quite yet. But what we instead did was we blocked off different chunks. And we'll talk about next week how we're actually going to move to a line and then, a curve and all kinds of fancy stuff.
Yeah, thank you.
Yep. Anybody else?
Just one last thing. The replace hotkey is Ctrl-H.
Great. Thank you.
That's about it for me. See you next week.
Yep. Cool. I will see you all next week. I'll post the code shortly. As usual, any questions? I know this is a lot to digest. Feel free to send me a Slack message. I will do my very best to get back to you. Thank you all for coming. I hope you have a great week, and I will talk to you in 7 days.
Thank you, man.
Yep. Have a great night.